Rolando Somma, who's going to be talking about his work on shadow Hamiltonian simulation. Okay, feel free to get started.
Right, can you hear me well? Yeah. Okay, so where are my slides? Let's see. Let me go back. Okay, so yeah, this is work with some usual suspects on quantum simulation. So it's theoretical work for simulating quantum systems. We call it shadow Hamiltonian simulation. And the idea is to do Hamiltonian simulation essentially in a different way. Okay, so it's a different approach for simulating, again, the dynamics of quantum systems. And it applies to systems that usually cannot be tackled with more traditional Hamiltonian simulation techniques. I will explain what I mean by that. Some of the examples that we can simulate with this technique are like free fermion or free boson models composed of exponentially many degrees of freedom, exponentially many modes. By that I mean that the algorithms are like efficient, like they pay a cost that is only logarithmic in the volume of the system. And for these problems, actually, we can prove that shadow Hamiltonian simulation can provide an exponential speedup, at least in this worst case scenario, right? So there's going to be some BQP complete problems associated with this framework that I'm going to explain. Beyond dynamics, shadow Hamiltonian simulation can be applied also to other related problems, like studying, for example, the evolution of the operators in the Heisenberg picture. And I'm going to make a quick comment about that, and also studying time-dependent correlations. All right. So other motivations. This is a novel framework for quantum simulation. We know that it already applies to other problems, so it's good to have these techniques. And in fact, we can prove there are many interesting BQP complete problems that fall naturally within this framework that we didn't know of before. And many quantum algorithms might never find practical applications. This is one of the reasons we're here. We expect that shadow Hamiltonian simulation is going to give us some interesting application domains, and we are actively working on that. So this is just a few examples that we can tackle with this technique. All right, so what is the traditional setup for Hamiltonian simulation or quantum simulation? This is what I call the Schrödinger picture technique. We have a quantum system that we need to simulate. There's a Schrödinger equation. We encode this on a quantum algorithm. We prepare some simple initial state. We try to mimic the evolution coming from this Schrödinger equation, but this unitary evolution operator, and then we make some sort of measurement. The measurement might determine some correlation function, some expectation value of an observable, and so on. This is not what we do in shadow Hamiltonian simulation. And instead of the technique involves that instead of having to deal with the full quantum state of the system, we're only going to track the information that is useful to us at the end, right? So this introduces the notion of what we call a shadow state. It's going to be like a mathematical construct that only keeps track of partial information of the quantum system. As a disclaimer, this is not really shadow state tomography or classical shadows, but somehow the intuition of having a shadow is similar in a way. Right. All right, so what are these shadow states that I mentioned? The shadow states are defined with respect to a set of operators that we do care about. This is the set S. Okay? So the shadow state can be seen in a way as a projection of the full state of your quantum system. This is rho. And we're going to project it to a manifold that depends on the set of operators that you're interested about. Okay? So for a given set S, formally, which involves M operators, O1 through OM, the shadow state of rho with respect to this set is going to be now a pure quantum state. Even if rho was a mixed state, the shadow state is going to be a pure quantum state that contains as amplitudes the expectation values of the operators in your set. Okay? So if your set is not complete, then shadow states are containing partial information about the quantum system. All right. Okay, so one thing that we already know is that because we only track partial information, maybe many quantum states of your system map to the same shadow state. And that is true. Okay? So it's like a many-to-one type of mapping, unless the set of operators is complete. Another thing that we know is that not all m-dimensional quantum states correspond to a valid shadow state, because we know that there are constraints between expectation values when we refer to quantum states, right? So shadow states are a manifold in this m-dimensional space that, again, the amplitudes encode information only about the expectation values of the operators you care about, not about everything. In systems of finite dimension n, so shadow states can be actually shown to be actual projectors. Okay, so this notion of a projection into a subspace is a correct one, and it's a projection of like two copies of the state. Taking two copies of the state and building this projection, again, depends on your operator set. If S were to be a complete set of operators, then shadow states can contain all the information of ρ. And indeed, we can show that there is a one-to-one mapping in that case. There is a unitary operator that takes copies of your state and maps it to a shadow state. So this V of S is not a projection, but it's a unitary in this case. OK, so just to warm up, a few examples of shadow states. We can consider, for example, a qubit system or a bunch of magnetic moments. Now my set of operators might be all the local operators, for example, all the angular momentum operators. This is what I chose as a set. Now my shadow state is only going to be a linear combination with amplitudes that are the expectations of these operators. For a fermionic model, I might consider, for example, quadratic fermionic operators. Now shadow states are these expectations of the quadratic operators, right? They contain those expectations as amplitudes. We can consider a full set of all poly operators on a net qubit system. This is how shadow states could look like. And again, this is a case where the full state of the system and shadow states are in a one-to-one correspondence because the set is complete. All right, so those are a few examples. What is that we can do with shadow states? Well, pretty much any computation like computing an overlap or measuring some expectation value, where what we obtain as a result is going to be a function that depends on the expectation values that you're following only, right? This is the only information that shadow states are encoding via the swap test or on some sort of measurement. These overlaps, these measurements usually correspond to some physical properties of your quantum system, like some energy, some fermionic modes, or something like that, some correlation functions. We can measure observables. Those could be like quadratic functions on the expectations. This is the result we could get. And again, when we do these measurements, those measurements are going to correspond to some interesting physical properties of your quantum system. All right. So as I will show, shadow Hamiltonian simulation actually concerns the efficient simulation of the evolution of these shadow states. The shadow states that contain only partial information on a quantum computer. Now, we want to do this on a quantum computer, so we are going to work with a Hilbert space dimension that is exponentially large in the number of qubits. And if your operator set, right, is, for example, something related to some local modes or some local sites and so on, then this would allow us to encode systems, the information of systems of exponential size, right? So for example, in the case of fermionic modes, if I consider all products of two fermionic operators, we have order n squared of them, n is the system size. Now, because I am allowing the Hilbert space dimension to be exponentially large, I can pick this n to be exponentially large. So this is where this power of shadow states is coming from. All right. So shadow Hamiltonian simulation asks this question. I have access to my initial shadow state, and I want to map it to the shadow state for a later time. So my quantum system is evolving under some Hamiltonian. Rho is changing in time. There's going to be a shadow state at the beginning. There's going to be a shadow state at the end. I want to find that mapping. So the question is, can we do this, right? So for example, if I have access to the initial shadow state and the Hamiltonian of the system, do I have enough information to specify the shadow state at a later time? So that's the main question. So what's your take? Any brave? All right, so the answer is no in general. And Robin would say, this is the end of my talk, and thanks for coming. So the answer is no in general, but if we satisfy something that we call an invariance property between the set S and my Hamiltonian H, then I can find this mapping, all right? So again, I mean, the setup is one where I contain partial information about the full quantum state. That partial information plus the Hamiltonian would allow me to determine the shadow state at a later time only if this invariance property is satisfied. Otherwise, the state doesn't contain enough information about, for example, the expectation values of other operators. So what is this invariance property? It's this mathematical relation that we have here. if I take every single operator of my operator set and I combine it with my Hamiltonian, and now I obtain a linear combination of the operators in the same set, then the invariance property is satisfied. For those that are familiar with Lie algebras, this is a standard property of Lie algebras, for example. Right? So I take my Hamiltonian that is acting on my quantum system, my full quantum system. I combine it with every single operator of my operator set. If I have this property on the commutator, we are going to say that we satisfy this invariance property. All right, so this invariance property is not always satisfied. Those are the cases that we need to discard, right? The shadow state doesn't contain enough information to determine at a later time. But when it is, then what we obtain is an evolution equation for the shadow state that looks pretty much as a Schrödinger equation. Okay? So my Hamiltonian now, this boldface H, is not the Hamiltonian of the system, but it's determined from the Hamiltonian of the system and the commutation relations, right? So these constants, structure constants that appear in the commutator, those are going to be the elements of my Hamiltonian, or my operator H of S. So it looks like a Schrödinger equation. Okay, so ideally, we would like to simulate this Schrödinger equation now using traditional Hamiltonian simulation on a quantum computer. But this matrix boldface H is not necessarily Hermitian all the time. Okay, so the evolution that you have there is not necessarily unitary. Shadow Hamiltonian simulation is actually concerned with the case where this boldface H is Hermitian. So we are going to make that assumption and explain a bit when that arises. And that's going to be the case in the examples that we study later. For example, if I have a finite dimensional system and my operator set is orthogonal, then I automatically get this hermiticity condition. For infinite dimensional quantum systems, where we can also apply the shadow Hamiltonian simulation technique, like bosonic systems, it is not always true that this HS, boldface HS, is Hermitian, but sometimes we can do some tricks with the commutator and change the basis and so on and transform it to a Hermitian operator. So this is discussed in detail in our paper. All right, so now what is the complexity of this technique, right? So again, I have shadow states, satisfy the invariance property, I'm assuming the boldface H is Hermitian, and I'm mapping the problem now to a traditional Hamiltonian simulation approach. So we can use all the machinery that's been developed in that context to simulate, to use it for shadow Hamiltonian simulation. For example, if we were to use something like quantum signal processing, we know that the cost is going to scale like linear in evolution time, linear in the, for example, the sparsity of this matrix HS, some norm of HS, and some logarithmic overhead that depends on the precision precision that you're trying to obtain. This also requires that the boldface H is efficiently accessible, right? And that happens, for example, when the matrices are sparse. That's one case. So we're going to have to make some sort of assumption on these commutation relations and probably assume that we have an oracle that outputs the properties of the coefficients in HS from these commutators. All right? So that's usually a case in many examples. All right, so a few applications. We can consider, for example, systems of exponentially many fermions. So if we have a Hamiltonian that now is quadratic in fermionic operators, we know these are integrable models, right? But these are of exponential size, so we are not going to simulate this efficiently on a classical computer. We have the Hamiltonian is quadratic of fermionic operators. We know the state is evolving under Schrödinger equation, but we are going to choose a specific set of operators as an example. For example, all quadratic fermionic operators, right? This Cj, Ck. So these are like Majorana fermions, for example. So the shadow state is going to be a state where the amplitudes, again, are the expectations of these quadratic operators. So they don't contain all the information about the quantum state. But we know that this invariance property is satisfied for these models because quadratic fermionic operators, when you start taking commutation relations between them, you don't leave that space of operators. And therefore, the shadow state is going to evolve according to this Schrödinger equation that I mentioned. Right? So these operators are also orthogonal and that guarantees that my ball phase H is going to be Hermitian. Indeed, the entries for this case of this ball phase H can be obtained efficiently from the couplings that appear in the Hamiltonian. So if I have like an oracle that specifies the Hamiltonian, all these interactions are appearing in there, then I can use that same oracle to simulate HS. All right, so if the initial shadow state can be prepared efficiently, and the interaction graph, for example, is sparse, so I have efficient access to HS, then I can perform shadow Hamiltonian simulation efficiently. So this enables, for example, efficient computation of many quantities involving exponentially many degrees of freedom now. An example is like computing some kinetic energy of some number of modes in your system, right? So that would correspond to some overlap between the shadow state and some other fiducial state. All right, so of course, I mean, there's a question of when is that we can prepare the initial shadow state efficiently. Not for rho we can prepare rho S efficiently. But there are a few examples worked out in the paper. Here I mentioned one where the initial state is like the vacuum state. There are no fermions in it. Then it's trivial to prepare the initial shadow state efficiently. Other shadow states, like for example, those corresponding to thermal gift states of your system can also be prepared efficiently as examples. We can move away from free fermion models and consider, for example, free boson models. Again, like we have a Hamiltonian that is quadratic in bosonic operators. I can choose as my set of operators like a linear set in the bosonic operators, for example. This is one case. The shadow state would only contain information about the expectation values of these operators only. We can also show that this invariance property is satisfied. Once you start computing quadratic bosonic operators with linear bosonic ones, you don't leave that space. Right? But in contrast to the fermionic case, as I mentioned at the beginning, this HS is not going to be necessarily Hermitian for this case. So a little bit more work is needed for addressing the bosonic example. So in the paper, we show how to solve this hermiticity issue by, instead of considering the operators that I mentioned in my operator set S, this linear in B, we have to take linear combinations of them. So if we satisfy the invariance property for each of those, we're going to satisfy the invariance property for a linear combination because of linearity. In addition, we can show that using a classical to quantum correspondence, we can use that same approach for simulating free boson models to simulate exponentially many classical oscillators. And this is an older paper from our group where we discussed that. I'm going to comment very quickly what is that we do in that case. So for this case of exponentially many classical oscillators, you can think of a network of masses connected with springs and so on. There's going to be an energy functional, so there is a kinetic term, there is a potential term, everything is quadratic. And the shadow states in that case are going to correspond to these vectors of exponential size, which are essentially the square root of the terms that appear in your energy. Now, because the energy is preserved in time, the length of this state is going to be preserved in time, and you can indeed prove that the evolution is unitary. Okay? So this is going to be the shadow state in that case, and we know how to simulate and evolve this state efficiently on a quantum computer. So now we can tackle these exponentially large systems of masses with springs, classical systems, by using this shadow Hamiltonian simulation formalism. All right, so for qubit systems, right, this is a standard example, we might want to consider, for example, the case where my set S is the complete set of operators. In that case, pretty much everything is like a one-to-one mapping, so this Hamiltonian HS is obtained from the true Hamiltonian of the system in that way. Okay, so it's like we are evolving two independent copies of the system individually. Right. All right, so that was about simulating quantum dynamics, but I mentioned at the beginning that we can move away from there and consider, for example, the evolution of operators in what we call the Heisenberg picture. Right? So in the Heisenberg picture, there is not really like a quantum state. We are concerned about the evolution of the operators per se. We have Heisenberg's equation of motion, right? And this is standard picture that we have. Like in the Schrödinger picture, we can think that we have state, we move in time, right? And then we measure some local operator. In the Heisenberg picture, we kind of like track back the operator and leave the state fixed at the beginning. So by using a similar encoding technique to what I mentioned for shadow states, we can now think about encoding operators on quantum states, right? So for example, I can have a ket O of 0 that corresponds to some local observable, for example. And now I want to create a quantum state that encodes the operator evolved at a later time. All right, so again, we're going to use the invariance property. Okay, so let's assume that we have a preferred set of operators, not necessarily observables. And let's say that my initial operator at time 0 is a linear combination of these, right? Now, my operators are going to evolve under some Hamiltonian h of t. I'm going to assume again that I satisfy this invariance property. And this again is going to define the same matrix that I was mentioning before, h of s, from the entries of these commutation relations. All right, so if we have the invariance property, then we can show that the operator at any time is also going to be a linear combination of the operators in the set S, right? This is what the invariance property is guaranteeing. So what we're going to do is try to go now the operator of t on a quantum state, where now the amplitudes of the quantum state correspond to essentially the coefficients that appear in the linear combination. This is one potential encoding, right? So now the question is again, how can we perform this evolution from a state that encodes the operator at the initial time to a state that encodes the operator at a later time? We can use the same machinery we developed for shadow Hamiltonian simulation, and you can prove that the Hamiltonian that generates the evolution is very similar to HS that I was mentioning, up to something we need to change the coordinates in time and conjugate, but it's essentially the same thing, the same object. Good. All right, so if we now can track the evolution of operators in a quantum circuit, in a quantum state, there's a bunch of new tasks that we can do, like, for example, unitary learning. As an example, let's assume that I have a black box unitary implements a Clifford operator that is acting on n qubits, right? So now what I could do is, for example, see how, using this encoding technique, how this black box unitary is transforming each poly operator. Where is it going, right? I can pick a set, for example, all the Z polys acting on the n qubits, all the X polys, again, acting on the n qubits, encode them in quantum states, and now do this like shadow evolution and see where they go, right? They have to go to now to quantum states that encode the new polys. This is a circuit that is going to do that type of transformation, all right? So if I now learn, I make a measurement on the world state, then I know, for example, where Z1 went to, where Z2 went to, X1, and so on. And that is enough information to determine what this Clifford unitary is doing. All right? OK, good. So that is an example of a stretch of this formalism to other operators. I also want to mention that there are many other situations that can be explored with this technique. So, for example, the prior observations that I mentioned about shadow states and shadow Hamiltonian simulation can actually be generalized by taking now products of operators in my, on my set S. Okay? So if I have satisfied the invariance property with S, then I'm going to satisfy the invariant property with products of S. What this allows us to do is now encode, for example, the expectation value of products of operators in S. This can be like correlation functions, like multi-time, multi-point correlation functions. So there's a generalization of the shadow state that I mentioned, and this is a generalization. And we know that the invariance property is going to be satisfied because of what I said about the commutation relations. And now I can have an equation of motion for these shadow states and contain more information that looks pretty much like this. It's like each of the registers is evolving under its own HS. Okay? So all this formalism can be extended to take into account correlations of more than one operator, and actually at different times, like Green's functions, for example. All right. So again, I mean, and the idea is that if the initial state, shadow state can be prepared efficiently, and if this HS can be simulated efficiently because probably is sparse or some property like that, then we can prepare a shadow state at a later time. Now we can make measurements on them, obtain information about these multi-time correlation functions, okay? And that would allow us to solve some interesting problems in physics. And again, this could apply to exponentially large systems of, for example, free Fermi models, free boson models, and so on, where traditional approaches could require exponential resources. We can also consider other type of encodings. Rather than encoding things on a quantum state, we might want to think about encoding things on a matrix, for example, what we call a block encoding. Right? So this is an example where my shadow state contains information about the product of two operators. There are going to be two indices. Now, a similar encoding but in a matrix would also do the job. If I know how the shadow state is evolving because I know my HFS, then I will know how my correlation matrix here is going to evolve. So this is interesting because shadow states, they have to be normalized, right? So whenever I make a measurement on them, then it's kind of like I'm losing signal on the expectations exactly because of due to this normalization factor. And that normalization factor might be exponentially small. When we move to this block encoding approach, we are working within a different axis model, and there's going to be some problems for which this rescaling factor is not going to be problematic. Block encodings have also their own rescaling factor they have to satisfy because they have to be embedded in a unitary operator. But that may be not that detrimental as for quantum states. Indeed, we have a recent paper discussing this issue a bit. Yes. All right, so as I said, once I encode things in a correlation matrix, I know if I knew the equation of motion for shadow states, then I would know what is the equation of motion for my matrix. Okay. So if I have access to the initial block encoding at time 0, and I have access to this HS, efficient access to it, then I can prepare C of t efficiently. So examples of these are like block encodings of correlation matrices of Gibbs states, thermal states, and now this approach could allow us to, for example, do dynamics of equilibrium of exponentially large systems of free Fermis or free bosons. All right, so a few comments on some future directions, and maybe some of you would be interested in working on these problems. I mentioned that shadow Hamiltonian simulation enables some exponential speedups, and that is true in the worst case, meaning that we can prove that there are some BQP complete problems we can solve efficiently with shadow Hamiltonian simulation. Okay, so that's evidence of an exponential advantage. Now, when we move to applications, like for example in physics, physics simulation, like wave propagation, some correlations, and so on, then these shadow states could allow us to compute like information about these correlations, but we're going to have to put some constraints, some physical constraints on the system. Okay, so what we do expect some useful applications for this type of problems. These constraints have to be taken into account when we really want to understand what the speedups between shadow Hamiltonian simulation and classical simulation methods are. Indeed, if we have, if our system interactions are local, especially local, then there is a light cone structure that's going to be, right? So the right picture to think about here is like maybe a big lattice, like 2 or 3 dimensions, and we're doing like a wave type of propagation, right? So I hit one end of the lattice and I let this wave propagate. There's going to be a light cone structure associated with that, and the volume of that light cone is going to depend on the evolution time. It's going to depend on the evolution time to the dimension of the lattice. Okay. So essentially, this is the yeah. I mean, it doesn't display well, but essentially, the complexity of classical algorithm for simulating this type of problem is going to be linear in space-time, right? So how much time you need, and what is the interesting volume of the system you need to simulate. So overall, the complexity is going to go with the time to the power 1 plus d. D is the dimension of the lattice here, right? And again, the interactions are local. Now, when we consider the shadow Hamiltonian simulation algorithm exactly for this problem, we know that the cost is mainly going to be linear in time. But as I said at the beginning, the cost in terms of the volume of the system is very mild. It's only going to be polylogarithmic, right? But we have this linear cost in time. So now the question is it really an exponential speedup for this problem or not? Well, this is a case where time and volume are polynomially related, okay? So we don't expect an exponential speedup when we put this locality of interactions constraint, But the type of speed that we do expect is this d plus 1 to 1. So for example, in dimension 3, we're expecting this technique to give you a quartic speedup. And this is some work, we're working on this type of applications currently. We don't know whether we can obtain bigger speedups, even under this condition, for higher order correlations. So that's pretty much open. And if we drop this locality condition, like for example, if we have type of dipole-dipole interaction where things decay with 1 over r cubed, then we expect that for that type of instances, the speedups are going to be more pronounced. All right. Good. So we can also move beyond unitary dynamics. Okay. So within the concept of correlation covariance matrices, in physics there is something called the Langevin equation. It takes a form like this, right? So this is like a dissipation matrix. So in this case, if you're interested, for example, in the fixed point of this type of equation, it can be proven that it maps to something that is called the Sylvester equation. It's a matrix linear equation of this form. So actually, we put the paper yesterday addressing exactly this same problem that can be solved efficiently, again, on a quantum computer. And this could allow us to obtain information about the fixed point of, for example, free fermion models or free boson models, okay? Because we satisfy this type of equation. All right, so going beyond, it would be really interesting to think about simulating interactive systems. So I mentioned the shared Hamiltonian simulation applies to systems like free bosons, right? Free fermions. So these systems are integrable. You cannot solve them classically efficiently when the number of modes is exponentially large, right? So that's where we get this advantage. But it could be ideally very interesting to move towards something that is beyond this type of systems. Okay? And again, we're working actively on extending this whole formalism to interactive systems by using various approximations like mean field theory and so on. Now, the challenge that becomes is that now the equations of motion, they cease to be linear. But we also have a number of quantum algorithms that apply to the nonlinear case. And this is essentially the roadmap that we're taking. All right, so another problem that is very interesting is seeing whether we can use this technique for simulating quantum field theories. And in fact, I showed you how to simulate some simple free field theories, like free boson models, free fermion models, and so on. Right? But the technique is different in a way that we are encoding information in a completely different way, right? So we are only encoding the information, the expectation values of the operators that we care about. Indeed, by using this approach, we simulate a free field theory without doing any type of approximation. We did that exactly. We didn't have to cut off this Hill space dimension or anything like that. So it would be really interesting to consider similar type of encodings and extend this result to, for example, 5-4, some interacting quantum field theory, by using now different type of approximation that people are used to that are more amenable to the encodings that we're considering here, okay? The shadow states. All right, so thank you very much, and I think we have like 5 minutes of questions. Thanks.
I think I might take advantage of being the guy carrying the mic to ask a question. So for time evolution,
Yep.
is this limited?